Hello. So welcome to YEA Big. And so today is today is the start of a new schedule. So we're starting from 5:30 now instead of 6. And so to start off, we have Zachary Cheng going over with a physics talk. Okay.
Okay, hello everyone. Welcome to our physics talk. Um, Today I'll be talking about a collection of problems that are roughly um, like based around the concept of conservation of momentum. Okay, so uh, here is the first problem. So we have two balls of equal radius and mass that are free to roll on the horizontal plane and are separated by a distance L large compared to their radius. And so one ball is solid and the other is hollow. And they're attracted by a force and they roll without slipping, and asks how far will the solid ball roll before the two balls collide. And so this problem isn't strictly conservation of momentum, as in you don't actually use it, but it's good to understand like the concept of how it relates to momentum. So it's like not that hard of a problem. So I'll give you 2 minutes to try it for yourself before I explain it. Okay, so um, it looks like this 2 minutes is over. So now I'll just explain. So basically, this is a ball, and it's attracted by this force, which we'll call big F, and it rolls without slipping. So there's a friction force from the ground, which it will denote by small f. And okay, yeah. So these are the only two forces on this ball. So we know we can write just F equals ma. So F minus F is equal to ma. Whereas the acceleration of the ball. And so now if we look at the torque that this friction force provides on the ball, that torque is Fr, obviously, where R is the radius. And this is equal to I alpha, which is equal to beta mr squared times alpha. And beta is some constant that differs for each type of shape. And beta mr squared is the moment of inertia I. And since it's rolling without slipping, then and here alpha would just be a over r, so this is equal to beta mr times a. And now we can just cancel r from both sides, and we get that this frictional force F is equal to beta ma. So we go back to our first equation here, and we find that F is equal to 1 plus beta times ma. So A is just equal to F over 1 plus beta times m. Okay, so now we realize that since we're trying to find the distance that the solid ball rolls, then since the distance, let's say d, is just equal to 1/2 alpha t squared, and since in this case the original velocities of both balls are 0, so there it's just 1/2 alpha t squared, and t is the time for which they roll, which is the same in both cases. So then the distance of d, like solid over d hollow, is just equal to alpha solid over alpha hollow. And for the question of what is beta, beta is just a dimensionless constant, and the moment of inertia of an object I is going to be equal to, like in like this case, for these nice shapes like spheres or like circles or whatever, it's going to be beta mr squared. Beta differs for each type of shape. And so yeah, it's something that's used when calculating like torque and like angular momentum and stuff like that. Anyway, so we get this should be a actually, not alpha. Yeah, so this is equal, the distance that they roll is the ratio of the distances that they roll is equal to the ratio of the accelerations, which is, and this we can see is equal to 1 plus beta of the hollow ball over 1 plus beta of the solid ball. And you should probably memorize these values for beta. This is equal to 1 plus 1 plus 2 over 3 for a hollow ball, and 1 plus 2 over 5 solid ball. And this is of course equal to 25 over 21. So then we found the ratio of the distances. So finding the distance is easy. It's just going to be L of the solid ball is just going to be equal to 25 over 25 plus 21 times big L, which is the distance it tells us in the problem between the two balls originally, and this is just 25 over 46 L. So that's the answer. And so like basically for this problem, the when we think of conservation of momentum, like when we use it, it's because there are no external forces on the system, like in a collision between two balls where the forces from each ball cancel out, right? So then we can use conservation of momentum. And here we can't, obviously, because there's an external force, which is the friction on the ball. But the mysterious force attracting both balls is the same. And that's like a concept that's used in conservation of momentum. So this is just a really like fundamental problem, I guess, but it doesn't really test your understanding of momentum, but more of like just forces. So yeah, that's the first problem. It's pretty easy. So now our second problem is this. Okay, so this is our second problem. A shell is flying with velocity 500 meters per second bursts into three identical fragments, such that the kinetic energy of the system increases 1.5 times. So what is the maximum velocity that one of the fragments can obtain? I'll give you guys another 2 minutes to try to work on this problem now. Okay, yeah. And therefore, this is problem 1 for those of you who came in late here. Okay. All right, so enough time has passed, so I'll just start explaining the solution. Okay, so let's look at this problem after the explosion into three fragments. Let's look at it in the center of mass frame. Okay, so we know that momentum is conserved because it's like an explosion. All the forces are internal, so momentum is conserved. So what this means is that if the shell is originally moving like this, so this is mb, that's the momentum, and we're looking at it in the center of mass frame. In fact, let's make this v0. So we're looking at this from center of mass, which means that our frame is also moving at v0. Then after it explodes, the fragments are going to go off into three directions. And this physics on this grade level, I'm not sure, but like it's probably something that you learned in physics in high school. So yeah. Okay, anyway, it explodes, and in the center of mass frame, originally the shell isn't moving, so like the v is 0. So after the collision, then the total momentum in the center of mass frame still has to be 0. So if this is the direction the first fragment goes, v1, then v2, let's make this another vector that's like this, and then v3 would be something like this, v. And so when we add these vectors together, they should form a triangle, because if they form a triangle, then we get that v1 plus v2 plus v3 is equal to 0, which is what we want, because then that means momentum is conserved. So these are what the vectors are like roughly like. And so now we look at the energy. So I'm going to skip the step with 1/2 m, because like that all cancels out really easily, and you can like probably figure it out yourself. So then when we look at energy, we can't do it in the center of mass frame, because because then we would get like positive values for v after the velocities of the three fragments after the explosion, and while for the energy before the explosion, in the center of mass frame, that would be 0. So we go back to the ground frame, and we would get v1 plus v0, and this is the center of mass velocity. Uh, okay, so I got a question that I think it's should this v1 plus v2 plus v3 equal to v0, and in this case it's 0 because v1, v2, and v3 are all in the center of mass frame, and yeah, so when we like add them together, it should be the same as before the explosion. And before the explosion in the center of, if we're looking at it as from a frame that's moving with the same velocity and in this with the same velocity as the shell, then what we would see is a stationary shell. Yeah, exactly. So then, but if we were looking at it from the ground frame, then yeah, it would be v0. So anyway, we get back to this equation for the energy. This would be v1 plus v0 squared, because that's the velocity of the first fragment if we're looking at it from the ground frame. This is v2 plus v0 squared plus v3 plus v0 squared. And this is equal to energy before the explosion would be 3v0 squared times, and now we multiply by 1.5 because it tells us that how much the energy increased. So this is equal to 4.5v0 squared. Okay, so now we can expand these squares and we get v1 squared plus v2 squared plus v3 squared plus 2 times v1 plus v2 plus v3 times v0 and plus 3v0 squared is equal to 4.5v0 squared. And yeah, so this v1 plus v2 plus v3 equals 0 from earlier comes into play now, so we just get that this part is 0. So now what we end up with is v1 squared plus v2 squared plus v3 squared is equal to 1.5 v0 squared. Okay. Okay, so now that we have this, we want to maximize one of these velocities. So let's just maximize v3. Okay, so and this is the wait, we're trying to maximize the magnitude of this. So if we to do this, we take v1 in this direction, and we can see that if we were to make v2 say this or this, then v3 would connect like this point back to the original starting point. And well, we know that from triangle inequality theorem that this would be less than v1 plus v2. So then however, in this case, they don't actually have to form a triangle because we could have v1 in this direction, then another v2 here, and then v3 would just go all the way back. And that's the maximum we can obtain. So then this would just give us v3 is equal to v1 plus v2. Okay, so now that we have this, we realize that now we have this, we look back at v1 squared plus v2 squared plus v3 squared is equal to this constant. And we can see that we want to make v1 equal to v2. And this is because if v1 were like larger than v2, then v1 squared plus v2 squared would get larger. Essentially, the minimum for v1 squared plus v2 squared occurs at v1 equals v2. And we want this v1 squared plus v2 squared to be minimized because we want to maximize v3 squared. So then this just gives us v3 equals 2v1. And this means that v1 squared plus v1 squared plus 4 v1 squared is equal to 1.5 v0 squared. And so then v1 squared is just equal to 1/4 v0 squared. And yeah, so v1 is equal to 1/2 v0. And it tells us in the problem that v0 is 500 meters per second. So v1 is 250 meters per second. And then we want to find v3 though, the maximum. So v3 is obviously just equal to 2v1, and that is, wait just a second, yeah, so v3 is equal to 2v1, and that is equal to 500 meters per second. Okay, so that's v3, but we're not exactly done yet because this is in the center of mass frame. We want to find the maximum velocity in the ground frame. And so remembering that the center of mass frame is moving at 500 meters per second, our final answer, v is just equal to v0 plus v3, which is 500 plus 500, so it's 1,000 meters per second. And so that is the answer to the second. Okay. And yeah, so does anyone have any questions about this problem? Okay, then so let's get right into our third problem since we only have 7 minutes left. So here is the third problem. We have 2 men that are standing inside a massless box and that are connected to each other through a massless and frictionless pulley system. So it looks like this. And there are people here, and each man is holding a ball of mass M that bounces. So they're out, and the system is at rest. So one man throws the ball vertically to a height h and asks what height with respect to himself can he throw the ball. Okay. So we only have 6 minutes left, so I'll just explain the solution here. Hopefully you can follow along. Okay, so when he throws the ball and let's say the ball leaves his hand with a velocity of v1, then the kinetic energy from that is 1/2 mv1 squared. And if it moves with upwards with v1, then he has to go down. Yeah, then he has to go down, and this with, let's say, v0. And from conservation of momentum, v0 is just equal to m over 2m plus m times v1. And this is because when he throws the ball, the whole system will have to like move as a result. So and the entire system's mass is 2m plus m. So yeah. So that's why it's 2m plus m on the bottom. And so then that movement will lead to, it has kinetic energy. So that's 1/2. And the mass of the rest of the system is 2m plus m and times v0 squared. And this is the work he does by throwing the ball. And yeah, so here's the problem. So this is the work he does by throwing the ball, and that gives us the maximum height it reaches, which is mgh as stated in the problem. Yeah, both of them have a ball. Okay, so yeah, okay, so now we have this equation. So we'll just solve it by plugging in this expression for v0. And so yeah, well, we can multiply both sides by 2, and we get mv1 squared plus m squared v1 over 2m plus m is equal to 2mgh. So now we cancel out the m here. Okay, here is the problem. Oh, I can paste it again down here. Okay, nice. Anyway, so now we can solve this for v1, and we get v1 squared is equal to 2gh over 1 plus m over 2m plus m here. Okay, so now when he lets go of the ball, his mass becomes mg. This mass is mg, but on the other side of the pulley, this mass is still m plus mg. So now the pulley will begin to move, and he'll accelerate, and obviously he'll go upwards with, and the total force here is m small mg. His acceleration is going to be this over the total mass, which is 2m plus m. Okay, so this is the acceleration, a. And now we're asking, the problem is asking for the height with respect to the man. So we have to do this in the man's frame. So to do this, we can just take the man's velocity as he goes down v1. Wait, as he goes down, it's v0. So the man's frame is moving with a velocity of v0 and an acceleration of a, moving upward with an acceleration of a. So then the ball, when we look at the ball in the man's frame, this ball's velocity, let's say it's v1 prime, is just equal to v1 plus v0. Yeah. Let me think just a second. Yeah, it's v1 plus v0, and this is equal to just this is just equal to v1 times 1 plus m over 2m plus m, or v1 times 2m plus 2 small m over 2m plus m. And his acceleration the acceleration as in a prime. And the question, I got a question that these are the initial velocities. Yeah. Yeah, this is the initial velocity for both the ball and the man when the ball leaves his hand. And the acceleration, a prime is equal to a plus g. This is because the man's frame is accelerating up while the ball is accelerating down with acceleration of g. So this is equal to g times 2m plus 2m over 2m plus m. Yeah. Okay, yeah. So now now that we have the ball's velocities, new velocities and accelerations within the frame, we can find the height it reaches above the man. And this would be, say, h prime, and we know that's just equal to v1 prime squared over 2a prime. And this is equal to 2gh v1 prime, yeah, 2gh over wait, let me see, yeah, v1, we have to go back to this for v1, 2gh over 1 plus m over 2m plus m. And that's v1 squared the height, I mean we don't consider like the height one right now, I guess, as in we just look at the initial velocities without accounting for the height. Yeah, like we just give them a variable name and then we can figure out how it relates later. So we get this and over 2a prime, which is, wait, v1 prime is v1 times this, so we still have to multiply by 2m plus 2m over 2m plus m squared, and all this over 2 times a prime, which is 2g 2m plus 2m over 2m plus m. Yeah, and then yeah, so now we can see some stuff cancels, like this this cancels out, 2g cancels with 2g, and we see that this is 2m plus 2m over 2m plus m here, so this should cancel out 2, and we're just left with h. And wait, let me think. With, okay, yeah, so then you just end up getting h. I'm not sure if that's actually the correct answer, but yeah. So yeah, I have some so I'll go check to see if this is actually correct, because I think it might not be, and I can like post a correction later because we're out of time here. And I also have like a few other problems that I didn't get to, and I can also post that in the Discord for you guys to look at if you're interested. So yeah, so we're out of time here, so yeah, that's my lecture today, and thank you all for listening.